Welcome to Brain Vision.
This is chapter 27, problem number 40. We are given a current carrying rectangular loop, a wire, embedded in an external magnetic field that is parallel to the surface of this loop. And the width is given to us as 5 centimeters. The length is 8 centimeters. Let's call it L. And the magnitude of the magnetic field is 0.19 Tesla. And the current through this closed loop of wire is 6.2 amps. Now, in part A, we are asked to calculate the torque generated by this external B field. So as you know, our equation is going to be the magnitude of current times the magnitude of the magnetic field times the area of the closed loop times sine of the angle between the normal vector of the area and the magnetic field. So as you know, normal vector is always perpendicular to the plane. So in this case, it's going to be out of the plane towards us, which makes the angle between A and B 90 degrees. So we can drop this sine term because sine 90 is going to give us 1. Simply, in order to calculate the torque, then we do I times B times area. As you know, it's a rectangle, so it's going to be the length times width. So we have 6.2 amps as our current, and the magnitude of the magnetic field is 0.19 Tesla, and length is 8 centimeters. So let's convert it to meters. In times, we have, I'm going to put it here, times 5 times 10 to the power negative 2, again, meters. When we do the calculation, what we find is 4.712 times 10 to the power negative 3 Newton meters as our torque. Now in part B, we are asked to calculate the magnetic moment. As you know, the magnetic moment is going to be the amount of current flowing through the loop times the area of the loop. So this is really straightforward. I times L times the width, right? So when we plug everything in, 6.2 amps times, well, let's put 8 times 10 to the power negative 2 meters times 5 times 10 to the power negative 2 meters, we're going to get 0.0248 ampere meter squared. Now, in part C, something interesting is happening. So in part C, or the problem, we are to calculate the maximum torque by keeping the wire length, overall length, meaning, the two sides and 2 widths and 2 lengths, right? We're going to keep this total length constant, but we're trying to maximize the torque by changing the shape of the loop. So if we want to maximize the torque by keeping the wire length constant, the only way to achieve this is if we have a circular loop, at which the circumference 2 pi r is going to be equal to our 2L plus 2 width, right? Because this is the total length of the wire. So now from this equation, if we divide both sides by 2, what we have is pi r has to be equal to L, the length times width, right? But when we're calculating the torque equation, we need, again, I, B, A sine theta. Again, sine, the angle is going to be 90 degrees, so that this term equals 1. We know the current, we know the B field, but the area this time, since we have a circular loop, then the area is going to be pi r squared. So this is what I'm trying to find. We deduce this information, pi r, from here. Then let's say r, by dividing both sides by pi, is going to be L plus W divided by pi. Now, if you're calculating the area in terms of L and W, then what we have is L plus width over pi squared. Now, since we have pi squared in the denominator, 1 is going to cancel this pi out. What we're going to have is the length plus width squared over pi as our area of this circular loop. Now we're going to come here and put that information I, B, instead of A, we're putting L over pi. Right. Now we're going to plug in for current and the magnitude of the magnetic field, so 6.2 amps times 0.19 Tesla. So it's going to be 8 times 10 to the power negative 2 meters plus 5 times 10 to the power negative 2 meters squared over 3.14. When we do this calculation, we're going to find the maximum torque to be 6.34 times 10 to the power of negative 3 Newton meters.